Hi, Stu Schwartz from MasterMathMentor.com. This is video AB29b. The topic is Riemann sums, and it covers the AB manual from pages 178 through 180. Midpoint Riemann sums have the advantage of having every rectangle very close to the true area because it over-approximates the area on one side and under-approximates the area on the other side. However, the computation for midpoint rectangles frequently is messier than the left and right Riemann sums. The advantage is, though, that we can get away with having fewer of them. We will go back to our example, finding the area under f of x equals 4x plus 12 minus x squared on the interval 1 through 5 using a midpoint Riemann sum with 4 rectangles. We still have our important values, x0, x1, x2, x3, x4, along the x-axis. However, now we need to find the midpoints between those values and build our rectangles there. So our first one will be halfway between x0 and x1, which is x0 plus x1 over 2. So our area will be base times f of x0 plus x1 over 2 plus f of x1 plus x2 over 2 plus f of x2 plus x3 over 2 plus f of x3 plus x4 over 2. Our specific case will be b times f of 1.5 plus f of 2.5 plus f of 3.5 plus f of 4.5. Our base is still 1, and now we have to plug 1.5, 2.5, 3.5, 4.5 into our expression, and as we said, it might be a little bit messier and you might need a calculator. We get 1 times the quantity 15.75 plus 15.75 plus 13.75 plus 9.75, getting an area of approximately 55. So the midpoint Riemann sum formula will be A will be B times sigma I equals 0 to 3 of f of x sub I plus x sub I plus 1 divided by 2. And if we were doing n rectangles in general, then A would be B sigma I equals 0 to n minus 1 of f of x sub I plus x sub I plus 1 divided by 2. Our fourth method of approximating the area is called the trapezoidal rule. It is based on creating trapezoids and not rectangles. It is a superior method of approximation because trapezoids use diagonal lines along the curve rather than the horizontal lines used by Riemann sums. As shown, the area of a trapezoid on its side, as shown in the figure, is A is equal to 1/2 the base times the sum of h1 plus h2. You can see at a glance that the trapezoid rule will do a very good job of approximating the true area under the curve. We still create our x values, x0, x1, x2, x3, and x4, which will divide our trapezoids. So our first trapezoid will have area b over 2 times the quantity f of x0 plus f of x1. The second trapezoid, b over 2 times the quantity f of x1 plus f of x2. The third trapezoid, b over 2 times the quantity f of x2 plus f of x3. And the fourth, b over 2 times the quantity f of x3 plus f of x4. We can factor out the b over 2 and get the quantity f of x0 plus 2f of x1 plus 2f of x2 plus 2 of f of x3 plus f of x4. So In our specific case, our area will equal b over 2 times the quantity f of 1 plus 2f of 2 plus 2f of 3 plus 2f of 4 plus f of 5. Since the base is 1, our area will be 1/2 times the quantity 15 plus 2 times 16 plus 2 times 15 plus 2 times 12 plus 7. And our approximate area will be 1/2 of 108, which is 54. So for n trapezoids in general, the area using the trapezoid rule will be approximately b over 2 times the quantity f of x0 plus 2f of x1 plus ... plus 2f of x sub n minus 1 plus f of x sub n. So except for the first term f of x0 and the last term f of x sub n, all the intermediate terms get doubled. So let's summarize. We are first assuming that f of x is positive. We'll deal with f of x being negative later. But for now, if f of x is positive, then the integral from x0 to xn of f of x dx, the area under the f curve, is approximated with n rectangles or n trapezoids. The base will always be x sub n minus x sub 0 over n, and we're assuming that the rectangles and trapezoids all have the same base. So the left Riemann sum, LRS, is equal to b times the quantity f of x0 plus f of x1 plus f of x2 plus ... plus f of x sub n minus 1, while the right Riemann sum, RRS, is equal to b times the quantity f of x1 plus f of x2 plus f of x3 plus ... plus f of x sub n. The midpoint formula is b times the quantity f of x0 plus x1 divided by 2 plus f of x1 plus x2 divided by 2 plus f of x sub n minus 1 plus x sub n divided by 2. The trapezoid rule is b over 2 times the quantity f of x0 plus 2f of x1 plus ... plus 2f of x sub n minus 1 plus f of x sub n. And you can easily show that if you add the LRS and RRS and divide by 2, meaning taking the average of the left Riemann sum and the right Riemann sum, you get the trapezoid rule. So if you have calculated the LRS and RRS, it is easy to calculate the trapezoid rule by simply averaging the two. Number 3 asks you to approximate the integral from 0 to 5 pi over 6 of sine x dx with 5 partitions using the left Riemann sum, right Riemann sum, and trapezoid rules. This is a good problem to test your knowledge of trig special angles. For all parts, the base is 5 pi over 6 minus 0 divided by 5, which is pi over 6. So for the LRS, A is approximately equal to pi over 6 times f of 0 plus f of pi over 6 plus f of pi over 3 plus f of pi over 2 plus f of 2 pi over 3. And for all the f's, you're taking the sine of those angles. So we get pi over 6 times the quantity 0 plus 1/2 plus the square root of 3 over 2 plus 1 plus the square root of 3 over 2. Getting the common denominator, we can write that as pi over 6 times the quantity 3 plus 2, square root of 3, all over 2. And the final answer is pi times the quantity 3 plus 2, square root of 3, all over 12. For the right Riemann sum, the area is approximately pi over 6 times f of pi over 6 plus f of pi over 3 plus f of pi over 2 plus f of 2 pi over 3 plus f of 5 pi over 6. Again, we're taking the sine of each of those angles, and we get pi over 6 times the quantity 1/2 plus the square root of 3 over 2 plus 1 plus the square root of 3 over 2 plus 1/2. This gives pi over 6 times the quantity 4 plus 2 square root of 3 over 2, and we get pi times the quantity 2 plus the square root of 3 all over 6. Let's do the trapezoid rule two ways. First, using the formula. So A is approximately equal to 1/2 the base, or pi over 12, times f of 0 plus 2f of pi over 6 plus 2f of pi over 3 plus 2f of pi over 2 plus 2f of 2 pi over 3 plus f of pi over 6. This gives pi over 6 times the quantity 0 plus 1 plus square root of 3 plus 2 plus the square root of 3 plus 1/2. And this becomes pi times the quantity 7 plus 4 square root of 3 all over 24. Let's show that the trapezoid rule gives the same answer as the average of the left Riemann sum plus the right Riemann sum. So if we average them, we get pi over 2 times the quantity 3 plus 2 square root of 3 over 12 plus 2 plus square root of 3 over 6. If we get a common denominator within the parentheses, we get pi over 2 times the quantity 3 plus 2 square root of 3 plus 4 plus 2 square root of 3 all over 12. And multiplying out, we get pi times the quantity 7 plus 4 square root of 3 all over 24, which is the same result as we got when we used the trapezoid rule formula. In differential calculus, we spent a great deal of time learning to take derivatives before we understood how the derivative could be interpreted and how to use it in real-world situations. The same is true with definite integrals. We have learned that a definite integral represents an area and how to take integrals of curves that involve straight lines and approximate them with Riemann sums. But other than the geometric meaning of area, what are they used for? We're finally ready to get some inkling of the applications of definite integrals other than pure geometry. If the x-axis is measured in x units and the y-axis is measured in y units, then the area under the curve is measured in xy units. So in our first example, our x-axis is measured in feet and the y-axis is measured in feet, and therefore the definite integral would be measured in square feet. But in the second example, the x-axis is measured in hours and the y-axis is measured in miles per hour. So multiplying hours times miles per hour, we get miles. In the third example, our x-axis is measured in hours, but our y-axis is measured in miles per hour squared. Therefore, the area under the curve would be measured in miles per hour. In the fourth example, the x-axis is measured in minutes, and the y-axis is measured in degrees per minute. Maybe it represents how the temperature is changing during the day. Therefore, the definite integral would be measured in degrees. Number 4 reads, a traffic light turns red and the driver stops the car in 5 seconds. Over those 5 seconds, the speeds in feet per second are recorded. The graph to the right plots those points with straight lines joining them. Find the area under the curve using a trapezoidal rule with 5 trapezoids, interpret the answer, and explain why this is an approximation. We are finding the integral from 0 to 5 of v of t dt. By the trapezoid rule, our base is 1, so our area is 1/2 times 1 times the quantity 88 plus 2 times 60 plus 2 times 40 plus 2 times 25 plus 2 times 10 plus 0. And that gives a numerical answer of 179. The units are seconds times feet per second, which is 179 feet. The interpretation is that it took 179 feet for the car to come to a complete halt. It's an approximation because we only know the data every second. We do not know what is occurring at a half second or 1.5 seconds. It's possible that the car might have sped up in that short period of time. We don't know. So this is definitely an approximation. If we want a better approximation, we need more data values. Number 5 reads, you jump out of a plane. Before your parachute opens, you are in free fall. While your speed increases, your acceleration decreases as you fall because of air resistance. The table on the right gives acceleration A in meters per second squared for the first 6 seconds. If time is measured on the x-axis and A is measured on the y-axis, find the area under the curve using a trapezoidal rule with 6 trapezoids and a midpoint Riemann sum with 3 rectangles, and interpret the area using correct units. Although not necessary, we plot the points and show the 6 trapezoids as well as the 3 midpoint rectangles. It should be clear that the 3 midpoint rectangles will do a very good job in approximating the definite integral. For the trapezoids, the base is 1. So the integral from 0 to 6 of a of t dt is approximately equal to 1/2 of 1 times 9.81 plus 2 times 8.03 plus 2 times 6.53 plus 2 times 5.38 plus 2 times 4.41 plus 2 times 3.61 plus 2.78. And we get 34.255, and that will be measured in meters per second. For midpoints, there are 3 rectangles, so the base is 2. So the integral from 0 to 6 of a of t dt will be 2 times the quantity. The acceleration at 1 second plus the acceleration at 3 seconds plus the acceleration at 5 seconds. We get 2 times 8.03 plus 5.38 plus 3.61, and that gives 34.04 meters per second. These values are the approximations of the speed after 6 seconds. So we're traveling approximately 34 meters per second, which is approximately 76 miles per hour. Number 6 reads, over a period of an hour, vehicles are lining up to go over a bridge. The table to the right shows the rate that vehicles join the line. Use the trapezoid rule to approximate the number of cars that have lined up in that hour. Although it is not necessary to graph the points, by doing so it is obvious that the trapezoids do not have a consistent base. So the only way that we can do this problem is to calculate the area of each trapezoid. So the trapezoid rule with doubling most of the components no longer works. So the number of vehicles is approximately 1/2 the base of the first trapezoid, which is 10, times the sum of their heights, 20 plus 25, plus 1/2 the base of the second trapezoid, which is 15, times the sum of their heights, 25 plus 45, plus 1/2 times the base of the third trapezoid, which is 15, times 45 plus 50, plus 1/2 the base of the fourth trapezoid, which is 5, times 50 plus 20, plus 1/2 the base of the final trapezoid, which is 15, times 20 plus 15. So doing the math, we get 225 plus 525 plus 712.5 plus 175 plus 262.5, and we get that approximately 1,900 vehicles have lined up in that hour. Again, though, we know that this is an approximation because we do not know the times in between. It could be that no cars have come in between, or many more cars have come in between. To get a better idea, we need as many data points as possible, which of course increases our work. Number 7 reads, a swimming pool contains 63,000 gallons of water, but is too cold, so the pool drains water while pumping in warmer water. The table to the right shows the rate that water is pumped in and the rate that the pool drains, both in gallons per minute, at various times over a 12-hour period. Using the trapezoid rule, how many gallons of water are in the pool at the end of the 12-hour period? Although a graph is not necessary, we show one to illustrate that the trapezoids do not have the same base, and they will have to be calculated individually. It also appears that the green data, which is the water being pumped in, has a greater area under it than the red data, which is the water draining out from the pool. Whether we are looking at the water coming in or the water coming out, for each trapezoid, the base is the same. For instance, the first trapezoid has a base of 2, the second trapezoid has a base of 3, etc. So for water coming in, we have 1/2 times 2, quantity 300 plus 200, plus 1/2 times 3, quantity 200 plus 300, plus 1/2 times 3, quantity 300 plus 400, plus 1/2 times 2, quantity 400 plus 200, plus 1/2 times 2, quantity 200 plus 100, and we get 3,200 gallons. For water coming out, we have 1/2 times 2, 300 plus 300, plus 1/2 times 3, 300 plus 200, plus 1/2 times 3, 200 plus 200, plus 1/2 times 2, 200 plus 150, plus 1/2 times 2, 150 plus 100, and we get 2,550 gallons of water that is being drained out. So the amount of water in the pool is 63,000, which was what we started with, plus the water coming in, which is 3,200 gallons, minus the water coming out, which is 22,550 gallons, and we have, at the end of the 12-hour period, approximately 63,650 gallons. Again, we say approximate because we really don't know what's happening between 0 and 2 hours, 2 hours, and 5 hours. There is no reason that these rates have to stay constant. So again, this is just an estimate, and the only way to get a better estimate is to get more data points. Number 8 is a slightly different type of Riemann sum problem. At 5 p.m., a subway train leaves a station with 20 people still on the platform, having just missed the train. Let P of t represent the number of people on the platform at time t, waiting for the next train, which will arrive at 5:05 p.m. Values of P of t are shown for every minute in the table below, where t represents the number of minutes after 5 o'clock. Part A, examining the graph to the right, find a left Riemann sum and describe the units in which it is measured. And then Part B, confirm that the second graph below has the same area using a Riemann sum and describe the meaning of this Riemann sum in real-life terms. We plot the 6 points as shown at t equals 0, 1, 2, 3, 4, and 5, and then construct 5 left Riemann sum rectangles. Therefore, since our base is 1, our area is equal to 1 times 20 plus 50 plus 80 plus 100 plus 140, and that will be measured in people minutes. The question is, what is a people minute? In order to understand a people minute, we redraw our graph. We extend our horizontal lines and eliminate most vertical lines. We also exchange the labels people and minutes. First, let us confirm that the areas are the same. The bottommost rectangle is 5 by 20. The next is 4 by 30. The middle is 3 by 30. The next is 2 by 20. And the top is 1 by 40. So do the math, and the area is also 390, and will also be in terms of people minutes. So now the interpretation. There were 20 people on the platform when the last train left, and each of them waited 5 minutes. There were 30 people who waited 4 minutes, 30 people who waited 3 minutes, 20 people who waited 2 minutes, 40 people who waited 1 minute, and the last 20 people who came at 5:05 didn't have to wait at all. So 390 people minutes represents the approximate total number of minutes people waited for the train. That is what a people minute is. While much of the time, Riemann sum problems involve a graph of time versus some rate. This type of problem is showing up more and more on AP exams. So students should always remember that a definite integral is always measured by the x units times the y units. On the screen, we see the graph of y equals x plus 2 minus 2 square root of x. And we'd like to find the area under the curve, the integral from 0 to 4 of x plus 2 minus 2 square root of x dx, with no error. No matter how many rectangles or trapezoids we use, there will always be an error. So our next video will be on the fundamental theorem of calculus, which will allow us to find the values of definite integrals exactly by strictly algebraic means. Stay tuned.